So deductive reasoning. So an argument is valid if and only if it takes a form that makes it impossible for all the premises to be true and the conclusion nevertheless false. Right? So it's impossible for that to happen. So if all the premises are true, the conclusion must be true. Now, the most common way of doing it is a direct proof. How many Latin students we got? Okay. There you go. We'll throw in a bit of Latin for us. That's what's known as modus ponens. It's what you're used to doing in geometry. But setting it up now with the language that we use in logic, we're saying, if we've got P, so we've got that statement, we know that, and we know P implies Q. So if we've got both of those things, we know P implies Q, and we've got P, so that implies Q. But let's actually prove that this is always a fact, regardless of whether P is true or false. This will always be true. So we have four possibilities that both P and Q are true, and both P and Q are false, and so on. So we'll fill in our truth table. So we'll fill down the P's and fill down the Q's. We work from the inside out. So P implies Q. Which one was the only one that was false in that one? P implies Q, the only one that is false, right, is the true implies false. So all the others are true. So now I'm looking at the blue and the P. So we're saying P and the blue. So and, true and true, true and false, false and true, false and true. So we end up with true for the first one, but all the others are false. So now we're looking at the green one with the Q at the end. So true implies true, false implies false, false implies true, false implies false. All of those are true. All of those are true. Remember we said the only one that was false in an if-then is if true implies false. So therefore, that is a solid proof. We can never get the situation where the conclusion is false, because that conclusion is true every single time. Okay, that proves our method of proof, which is great because we've been using it for years now, so we'd be in trouble if we couldn't. The argument is valid if it's impossible for the premises to be true and the conclusion to be false. Now, our final conclusion is this red one here. And I just showed that actually it doesn't matter what I do here. I will always end up with true. I'm never going to get a false conclusion. Now, just at the end of that, I could build on that because I might have a situation where I've proven P implies Q, and then I've also proven that Q implies R. So if I've got both of those, then it's fair enough to conclude that P implies R. Let's do a proof. I'm going to prove that if a number is odd, then its square must also be odd. Let n be an odd integer. So I need to set it up so it's an odd integer. How can I do that? Well, I'll say it's going to equal 2k plus 1, where k is some integer. That will ensure I have an odd number. I could have said 2k minus 1. I suppose I could have said 2k plus 53 if I wanted to, but I mean 2k plus 1 is nice and easy. All right, well let's square in. If I square in, I've got 2k plus 1 squared. Square that out, 4k squared plus 4k plus 1. Remember, I'm trying to show this is odd. So I'll leave the plus 1 by itself, and then I can factorise the rest, and I get 2 times 2k squared plus 2k. Well, if k is an integer, then 2k squared plus 2k must be an integer. So therefore I have 2p plus 1, where p happens to be 2k squared plus 2k. But yes, that is an integer, and that was what we defined an odd number to be. So hence, if n is odd, then n squared is also going to be odd. So that's a direct proof. How about this one? Prove that the sum of the squares of 5 consecutive integers is divisible by 5. So if you have 5 consecutive integers, the sum of the squares must be divisible by 5. Now, I just point this out. If P and Q are both integers, and I know Q is divisible by P, then there must exist a number, another integer, such that Q is equal to P times N. I'm going to let Q equal that. It's 5 consecutive squares, but rather than going n plus 1, n plus 2, it's actually going to make my life a lot easier if I start at n minus 2. If I go n minus 2 squared. Because if we were to expand that all out, which I'm not going to do, because we know the pattern, I know that the n minus 2 squared with the n plus 2 squared, that middle term is going to cancel out. So all of this should create 5n squared. They're each going to have n squared. All of the middle terms will cancel out, and I'll get all the squares. So I'll have 4 and 1 and 1 and 4, which adds up to be 10. We're trying to show it's divisible by 5. So if I factorise by 5, then we get n squared plus 2. But yes, n squared plus 2 has to be an integer if n's an integer. So we have our result. Hence the sum of the squares of 5 consecutive integers is divisible by 5. So that's a direct proof. Now we're going to do proof by contraposition. And again, for our Latin fans, that's modus tollens. Modus tollens. That's basically what we saw in that multiple choice question we just did. So not Q implying not P is equivalent to P implying Q, because sometimes that is easier to work out. So for instance, something like this. We're going to prove that if 2 to the power of n minus 1, where n is a natural number, if that's prime, then n is prime as well. That's really hard to do, because how do you define the primeness? It's too hard. So we're going to do it the other way around. So if I let n equal p times q, and then pq is an element of the natural numbers, and p and q are not equal to 1. In other words, what I'm saying, n is not prime. It's not prime, because it's made up of 2 prime numbers. Now, 2 to the power of n minus 1, I can now rewrite as 2 to the power of pq minus 1. Just playing with my index laws now. So 2 to the power of p, all of that, to the power of q minus 1. Now, do you remember our factorisation? Right? A to the power of n minus b to the power of n. That's what I'm using here. So we would have in the first parentheses 2 to the power of p minus 1. In the second one, I'd have 1 plus 2 to the power of p plus 2 to the power of 2p. And the powers are basically going up. And the last one would be whatever q minus 1 times p is. So it equals p times q. They're both going to be integers, where p is 2 to the power of p minus 1. That can't equal 1, because we're raising 2 to the power of p, and where is it? We define p is not equal to 1. So therefore we can't have 2 minus 1 and it becomes 1. The smallest we could get would be 2 squared minus 1, which is 3. And then in the second one, well, that can't equal 1 either, because we're starting off with 1 and we're adding things to it. So I know neither of those are 1. Thus, if n is not prime, that's what I started with, then 2 to the power of n minus 1, I've just shown that's not prime either. Hence, if 2 to the power of n minus 1 is prime, then n is prime by contraposition. All right, now let's look at, and this one's really cool in Latin, by the way. Now let's look at proof by contradiction. Reductio ad impossible. So this is an indirect proof. That's basically, there it is in logic. So we're saying if we don't have the p implies q, we have the negation of p implies q implies r and not r. So in other words, we want to prove p implies q. But remember, in proof by contradiction, we assume the opposite. So if I negate the p implies q. So if I've got that and it ends up with r and not r, it doesn't matter what r is, but I can't have both r and not r, there's my contradiction. So that then allows me to imply p implies q. So that's basically the logic behind proof by contradiction. Let's prove it then with a truth table. Again, remember we should end up with all of them being true. So P and Q, well R I filled in, because we know it doesn't matter what R is. Every one of those is going to be false. You can't have R and not R. So at the end there, I'll just fill in the true falses, copying over. And may as well do that one as well. So in purple there, remember, the only time it's going to be false is true implies false. Okay, now let's go back to the first one. The negation of P implies Q. Well, I did P implies Q over here on the right. So the negation is it changes the logical value. So it now becomes false, true, false, false. All right. So what's next? We want to do this one here next, don't we? It's inside the parentheses. So implication, remember the only one that is false is true implies false. So that now I've got it in green. But the second one would be the false one. So now I'm going to the green one, and it's the purple one. The only one that is false is true implies false, and we don't have that anywhere then. So they're all true. So it is a solid proof. That's why it works. Proof by contradiction. So let's do one. We're going to prove that the log of 5 base 2 is an irrational number. Is an irrational number. Alright. So we're going to assume the opposite. I'm going to assume it's a rational number. If it is a rational number, then I can write it as a fraction where P and Q have no common factors. Or another way of saying that is coprime. Remember the term coprime? So coprime just means all of these numbers, in this case there's only 2, but the biggest number that goes into all of these numbers is 1, basically. Means coprime. So 2 to the power of P on Q is equal to 5. Playing around with that, I get 2 to the power of P is equal to 5 to the power of Q. However, the left-hand side must be even, because I'm going to go 2 times 2 times 2 times 2 times however many times, but I'm always going to end up with an even number. The right-hand side will always be odd, because I'm going to go 5 times 5 times 5 times 5. I'll always end up with an odd number. So I've now contradicted myself, so therefore, yes indeed, it must be irrational. Prove there are no integers, a and b, such that 18 times a plus 6 times b is equal to 1. You cannot substitute numbers into that for it to happen. So I'm going to assume, remember I'm doing the contradiction, I'm going to assume that actually it can happen. So there does exist an a and b such that 18a plus 6b is equal to 1. And you might be thinking, hang on, of course you can't. How are you going to get 1? But remember, I'm not saying positive integers. I'm saying integers. So I could use negative numbers. I'm still saying it's still impossible. Can't do it. All right, but if it is possible, well, then we know 18a plus 6b is equal to 1. And I'll factorise that. That factors to be 6 outside of 3a plus b is equal to 1. So 3a plus b is equal to 1/6. Now we've got a problem there, because we defined a and b to be integers. So how do you add 3 times an integer plus an integer and get an answer of 1/6? You can't do it. So 3a plus b has to be an integer, so it can't equal 1/6. There's my contradiction. In one effort I'm saying it's equal to 1/6, in another I'm saying it's not equal to 1/6. Can't be both. So hence, there's no way we can have integers a and b such that it equals 1. Let's show you the one from last year's HSC. Right, so the first one of this new course. In a set of integers, P is going to be the proposition. If k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. It then said, prove that proposition is true. So I just did a direct proof myself. So I'm going to say, well, okay, I'll let k plus 1 equal 3p. They've told me it's divisible by 3. So I'm going to say it's 3p, where p is some integer for all k, and they're also going to be integers. K is going to be integers as well. Now, k cubed plus 1, we know the factorisation. K plus 1, k squared minus k plus 1. Well, k plus 1, remember I defined it to be 3p. So it's 3p outside of k squared minus k plus 1. So I can write it as 3 times something. It does have a factor of 3. I mean, k squared minus k plus 1 has to be an integer because k is an integer. So thus I have proven that if k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. Part 2. Write down the contrapositive of the proposition. So the contrapositive is where you negate the reverse of the implication. So it will be, if k cubed plus 1 is not divisible by 3, then k plus 1 is not divisible by 3. And it finally says, well, now write down the converse. So that's the one that reads backwards. And state with reasons whether that converse is true or false. So there's the converse. Read the implication back the other way. So if k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3. So basically, if I'm going to do this by contraposition. So again, I'm saying that P implies Q is logically equivalent to not Q implies not P. And just to make it 100% clear, I'm saying, well, P is going to be my statement. K cubed is divisible by 3. Q is going to be my statement. K plus 1 is divisible by 3. All right, we'll go back to this k cubed plus 1. We know k cubed plus 1 is k plus 1, k squared minus k plus 1. And I'm going to play around with the factorisation of that. So what we've ended up with is something that's not divisible by 3. Because remember, we said k plus 1, well, I'm going for the contraposition. I'm saying k plus 1 is not divisible by 3. So therefore, this factor of k plus 1, I can't pull out a factor of 3. Look at the second factor. Can I pull out a factor of 3? Well, again, I can't, because whilst it is a factor of 3k, it's not a factor of k plus 1 squared, because 3, we said, was not a factor of k plus 1. So if k plus 1 is not divisible by 3, I know k plus 1 squared is not divisible by 3. Therefore, k plus 1 squared minus 3k is not divisible by 3, which means the whole thing is not divisible by 3. So in other words, I've just proven that if k plus 1 is not divisible by 3, then k cubed plus 1 is not divisible by 3. Therefore, k cubed plus 1 is divisible by 3. Oh, sorry, if k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3.
By contraposition.
By contraposition. Playtime.